Welcome all, this is Saud. I'm going to give here a practical demonstration to explain the way how to connect devices with Modbus protocol using RS232, and of course we're going to go through the RS485 connection as well. Quick introduction to the components and devices involved in our demonstration. Here we have it's a control module. It's going to act as the slave device in this case. This control module is powered by 110 volt. That's why I'll need a stepping down transformer to step down from the 220 volts and give 110 as an input to the board. Important thing to mention here, that whenever we are involved with high voltage applications, so we need to be very alerted and careful and avoiding touching the high voltage portion. Another part, it is the master device. In this case, it will be both the laptop plus the Modscan32 application, which is going to act as a master to pull the target board. I have here the RS232 port to the slave device using RJ12 connector, and this is connected all the way by using the data link cable to the input of the PC, the DB9 RS232 with 9 pins, female connector. So this is going to the input of the PC as a master device. And I have just connected LEDs on the TX and RX cables just to see the activity in the bus. Of course, in the actual installation, it's not very advisable just to put an LED direct connected, because this might load the signal and it might cause other problems. So it can be connected in the right way by using buffer circuits. So the red LED is connected to the transmit, which is pin 3 in this case, and the green one is connected to the RX receive data, which is pin 2 in the input of the DB9. So this will be helpful really to see the activity of the TX and RX during our check. RS232 mainly use 3 wires, which is TX, RX, ground, but it can be more if handshake is required. So mainly we have the ground connection and the receive data and TX data. Of course, like in our case here, we have the RJ12 connector, but it can be other type, like this type of connector. So it will be a termination where I terminate my wires, and then I need to know the pin out of every input to connect it right. And some of course the control modules also, they can have just a DB9 connector similar to this. So with mainly what we need for the RS232 is the pin 2, which is the receive data, and pin 3 is the transmit data, and then the ground common, which is pin 5. But sometimes the other signal might be required if the handshaking is the way to connect on such devices. And in the DB9 input, particularly also the pin out is standard. For example, this is for the PC connector where we have pin 2 as the RX in this case, and pin 3 as the TX, then pin 5 is the ground. If RS485 connection is used, then it is normally using 2 wires only, plus and minus, sometimes they call it A and B. With of course RS485 is not available at all with laptops. With older laptops and PC, you can have the DB9 RS232 but with the newer one it's not there anymore. They substitute and they use USB input now, and in fact you can instead now use USB to serial converter to achieve either the RS485 or RS232 connection. With RS485, as we can see from this sketch, we have only, as we mentioned, 2 wires. So the master is pulling the slaves, and that's why the RS485, it allows multi-dropping, so I can have more than one slave pulled by one single master. Of course, every slave it will have its own address. Another component, it's really important to be considered when connecting RS485, what we call end-of-line termination. We will need 2 of them at least. So one should be at the master side in the beginning of the bus, and the other one should be at the last device. The termination resistor can be around 120 ohm. In our demonstration, as I mentioned, we'll use the RS232 connection, but the concept should be the same, of course, with 485, and the way how we are going to check it should be also useful with the 485 connection. RS232, it can go to theoretically 15 meters. Slightly it can go higher than that depending on the baud rate and on the quality of the cable, surrounding noise and all this. The 485, it can be, in fact, it can go longer. It can go to even 1.2 kilometers, and also the same case depending on the baud rate which is being used. All these concepts and parameters we are going to explain during our demonstration to explain the effect of the baud rate and the other communication settings. Modscan application, it's a useful tool to check the connectivity and the response from the Modbus devices. Like in our case here, we have the control module, and it can be, in fact, let us say a PLC, or it can be a flow computer, or it can be an RTU. So with Modscan, it simplifies the steps to check the communication status to the devices, because I'll have all the indications visible to me. So let us say we have a master device, DCS for example, it's pulling number of devices or number of flow computers, and I am not getting a response from these devices. So it will be useful really to isolate these devices and connect them through Modscan to check the communication status of them. Then once I get the communication proven and working fine, then I can connect it back to the master device, because there is a lot of settings involved on such communication link. So with Modscan, it will be really easy for me to examine all and to prove that the communication is okay. Before starting the Modscan32 demonstration, I'd like to give a brief explanation of the concept of the Modbus protocol. It's very important to understand the concept of the Modbus protocol and the content of the message. In certain level of troubleshooting, I might need really to analyze the Modbus message using, let us say, protocol analyzer application to see content of the Modbus message, the response and the query from the master. Modbus is in fact a language. We have two type of Modbus protocol: the Modbus ASCII and the Modbus RTU. The Modbus ASCII is 7 bits. The Modbus RTU is 8 bits. Nowadays, mostly Modbus RTU is in use. So, at the beginning of the message, I have the address, and this is 8 bit. So this is the address of the source and the destination as well, okay, of the query. I have then the function code. The function code, it helps to identify the type of the required data. So we have number of function codes. We have coil status. We have function code 2, the input status. We have the function code 3, which is the holding registers, and then 4 is the input registers. Okay, so digital out, digital in, and analog out in as well, and then analog in input. Okay, then after that we have required data. So it will send the starting register, requiring the starting register, and then the number of register. Let us say I require 10 register. Then the starting register, I have to identify here what's the starting point of the register number 1, and then I have to put 10, which is 10 register in my case, for example. Then we have the CRC check, which is the cyclic redundancy check. This is an error check technique used by the Modbus RTU. While in the Modbus ASCII, they use the LRC check, which is the longitude redundancy check. This is the message of the query from the master, for example. Then we have the response back from the slave, which again should contain the address, okay, in this case the address of the slave, to tell the master that the response is from that slave. Then of course the function code, and function code, in fact it's also 8-bit in this case. Then the data respond itself, so it will respond back with the required data which is being requested here, with the every register and the values on those registers. Then again, of course the CRC, which is the error checking message. So with Modbus register, we have ranges for every type which it needs to occupy. So in this case, the coil registers, they're using the range from 1 to 9,999, and discrete input, the detail input, it's using from the range of 10,001 to 19,999, and the input register, in this case the analog input, is using the range from 30,001 to 39,999, and then we have the holding registers. In this case, it's the analog input output, occupying the range from 40,001 to 49,999. Okay, let's start setting up the Modscan to read a few data from the target slave device. Analog data input register should be the easiest one to start with. Okay, I don't expect to get really any values from the target device currently, because no inputs are connected to the device, but we might get few dummy values. It doesn't matter, we don't care what values we are getting, as long we are going to establish the communication link between the Modscan and the target device. So few things we need to set up here in the first screen to start the initial settings. We need to specify the starting registers, at what register you want to start pulling my slave device in this case. So normally we need to have the manual of whatever slave device where it specifies the data against the Modbus register. So I'll use that list, that table, to establish the mapping at which I can really select the data to be read from the slave device. So okay, I know on this device I can start with Modbus 30258. This is analog input register. Okay, so let's type that one in the address field, 30258. As you can see here, yeah, I have double 3, which is not supposed to be there, because the Modscan automatically, as long as I already selected the data type as an input register, it knows at which range it should fit that one. So it means I don't need really to specify whether it is 3 or 4. As you know, 40,000 is for holding register and 30,000 is for input register. So I don't need to specify whether it is 3 or 4 directly. Then I'll put 258 in this case. And as you can see here, it is 30258 starting. Very good. Okay, then I already set it the starting register to start pulling the target device, and then I need to put the length of how many registers I need to pull and I need to display here. In my case 10 should be fine, so 10 register. Good. So yeah, so you need to specify the length of the register. Okay, there is another important parameter here to be set. It is the device ID, the address of the device. As we mentioned before, we might have multiple devices multi-dropped in one single communication bus. So it means every device, it should have a unique address. Okay, so the master is going to know to which device it's really talking and pulling the data. And this is one of the Modbus protocol requirement, in fact. So in our target board here, I already set it the address of this target device to 1. So we'll specify here as 1. Good. As we have only one device, we are pulling one device through the RS232. Then I need to specify the data type. Okay, we have a multi-drop here. It's very easy. Then I can specify, I can write coils. So I can write digital out to the slave device if I select coil status. I can read input status, digital input from the slave device. I can write analog holding register to the target device. I can read analog from the target register through input register. So in my case here, I'll of course select the input register as I am trying to read analogs in this case. Up to this point, I am done with the settings at the first page. Okay, then I need to go to the next step. With Modscan, we have the tab connection. So then I need to connect, simply connect, trying to connect to the target device. Then it will open another window for few extra settings. Okay, with Modscan, in fact, I can use Modscan to connect to the target or to the slave device through TCP/IP, Ethernet, and then I can specify the IP address to talk to the slave device. But in our case here, we don't use the Ethernet connection as we are using the 232 link. So I'll just use a common option. So the common is assigned to the RS232 port of the laptop. Okay, then good, that's done. Then we Yeah, we need now to specify few other very important parameters. The baud rate. The baud rate is the speed at which the master device is going to scan the slave. So in my case here it is at 1200. It can be anything, it can be higher or lower than that, but depending on the system capabilities. I mean, I need to know really the limitations of my slave device and the master device, and limitation of my connection, the cabling and all this aspect to have really a reliable communication link. In that way I can easily decide what is the most suitable. I don't need to go to the higher if I don't need. It's not necessarily. So in my case here I set my target baud to 1200 bits per second as a data rate. Then I need to specify the word length. Of course we're using Modbus R2, in this case it is 8-bit. Then the parity, it's a way to make error checking and of the Modbus message. So it can be, we have few settings there, it can be odd or even, but in my case I'll select none. So as long these settings are matching between the slave device and the master device, then everything should be fine. So stop bit also need to be set. So this is the stop bit of the Modbus message itself. So it can be either 2 stop bits or 1 stop bits. So in my case I already set the stop bit on the slave device to 1. Good. So we are done. Yeah, still we got another important parameter, which is the protocol. In our case here, our example, we are using Modbus R2. Another few parameters, so we're going to come to them later on. As now, we can go ahead and try to establish the link at least to the slave device. So we'll click OK. Then again we click OK on this. Yeah, and we can clear the pulling counter to really see. So the Modscan is pulling now. Okay, and we can easily see that through the TX LED, the red one. So it's really pulling now, but there is no response from the slave device as it is off currently. It's off. So as I switch on this one with these settings, which I just put, because all I am sure they are okay, I should start getting the RX LED also on, and the response back from the slave should come. So let's switch on the device. Yeah, so we'll go back now and see. Very good. So I'm getting now the response back. So the green LED is also coming after a few milliseconds of the red LED. So it's pulling and getting response back easily. And I can see here that I'm really getting a response. So the response counter is also counting up, and I'm getting few values. Of course this is dummy values, I don't care anyway, because yeah, so the link is established, so it's healthy and on. Few useful observations. As we can see here, the time length of the respond back from slave, the receive signal. Yeah, if for example we increase the number of registers, because I'm pulling 10 right now, let's say I put it to 40. So then observe it now, we can see that the receive time length is longer, because I have more number of registers to reply back from the slave device. To see the difference, I'll just put it to, let's say, 1, then I flicker to 40. So see, this we're putting only 1 register. I'll change it to 40. As you can see, stay longer now because we have more number of registers to reply back. As I mentioned before, there is few other settings. Let's go back and check what they do. Okay, let's connect back. Good. Yeah, it was under the protocol tab. Yeah, we have what we call a slave respond timeout. This type of settings, in fact, they are normally there with every master device. In our case, we have the Modscan here, but if I've got another master device, let us say it is PLC, DCS-R2, then I'll also have these settings, and I'll need to also set them. The slave respond timeout is the amount of time the master will wait for the slave respond. Otherwise, it might terminate the communication or take some other action. So in our case here, we have 1000 milliseconds, which is reasonable. The delay between poles. So delay between pole settings is also important because depending also on the limitation of the target device or the slave device, I need to give it some time between from pull and the next pull. So it will have enough time to respond the message back. So we can see the effect of this one. Currently it is 500 milliseconds. Let's say we put it shorter time, 50, and see how the response is going to be. Okay, it's 50. Okay, so I need to. This is the interval time between the pulls. As you can see, let's now put it to longer time to see the effect. Okay, disconnect and then connect to get the window back. Let's put it to 2000 millisecond. 2000 millisecond to see the effect. Okay, good. Yeah, as you can see now, it waits longer to pull the slave device. So it wait longer because the interval between the pulls is longer. So I need really to know the limitation of the slave devices and also to take consideration if I have got multi-drop devices within my link. Let's experiment the digital signal and the effect of sending digital command from the Modscan to the slave device. I have connected an LED on one of the digital outs of the slave board to see the status of that digital out. Digital outs can be used for anything. It can be used to let us say start a motor or start a compressor or reset the alarms to the slave board, or it can activate an external relay depending on the application. So we'll set our digital out. Okay, that's at 538. So I'll put just two register. So I'll put 2. Okay, and then I need to change it to coil status because I'm sending an output now, digital out. So it should be through coil status. Good, so it's responding now. Mark normal. So I can activate an output. So so simply you need to click on the register. It will open another window. Then I set it to on. 1, and I have to see the effect on the LED. So I'll update. Yeah, so it's on. Okay, so then I'll just set it back to off. So I'll go to the next register depending. Sometimes you can switch on and off through the same register, so sending 0 or 1 on the same register. And some devices, they use 2 separate registers, one for switching on and one for example, switching off. So I'm using the second register, so I'll switch on the second register to, in fact, deactivate the signal. Okay, yeah, it's off. So that's the way how I can send command from the Modscan to the target board. It's very good tool really to test the functionality of the response of the external device. Let us say it's connected to the slave board. So this is the way how I can check it. Another useful tool to talk about is analyzing the Modbus message content. We can go through the setup, then here we have a display option, then we have 2 display options in fact. As I'm displaying my values now in integer, so I can display it as well in binary format, for example, if it's required. So the data, it will be in binary format, or it can be in any other available format. It can be floating point or the rest of the format. So this is the show data. So this is what it will show me the data in different formats. I'll then switch to the show traffic, which will show me the Modbus message, how it's really flowing from the master to slave and back from slave to master. I'd like normally to view those data in hex when I really check the analyze of the Modbus message. So I'll switch it to hex, then I'll go to setup again and show traffic. So now we'll start getting this is the messages as it's going through from master to slave and back from slave to master. I'm going to pause the connection now just to go in more detail on this content. So if we go back to what we have explained before on explaining the Modbus message, as we mentioned, we have the address, then the function, then a starting register, number of registers, and the CRC check. So let's check if this is really true here. So the white background one is the request from the master. So it is address 1, correct, true. So it's pulling using address 1. Then the function code 04, which is read input register 04. Then we have 0101. This is a starting register in our case. If you convert this from hex to decimal, it is 257. It is 258, our starting register. In fact, a standard here is in Modscan is one offset, so this is correct. Okay, starting register is 257. Then the number of registers is 10, 000A in hex, so if I convert it to decimal, it is 10. And then the CRC check. Okay, this is the request from the master. The response from slave, the same. If you see, this is the response starting 01 again, because the slave address also is 01. And then function code 04, read input register, correct, the same. Then the data itself, because if you go back to our document and let's check the response back, if you see a correct address, then the function code, then the data which is being requested previously by the master, and then the CRC checks, of course. The tool of analyzing the Modbus message is really useful and needed in certain level of communication troubleshooting if I suspect a mismatch in communication between devices. And this application, I mean the protocol analyzer, is available in fact in it can be a standalone device, and sometimes it is a PC-based application where I can put it through the communication link and analyze my messages. This is all about the Modscan setups and in fact connecting the RS232 and RS485 data link. Few comments about the actual installations to be always considered. As I mentioned before about the RS485, the end of line termination is really advisable to be used, as this helping to reduce the signal reflections in the line, so it reduces that and kill it. If signal reflection is there, then it will attenuate the actual signal, and if the signal is attenuated, it will be weak, and noise will attack the communication link if noise is available, and definitely it will lead to more number of retries in the bus from the master to slave. If this happens, then the performance of the communication link is going to really go low, or it might lead to total communication loss. In regard of RS232 installation, it's advisable to consider the cable length so it doesn't really exceed the limit. The shield grounding connection should be in one point, not in multiple points, as it can lead to ground looping and noise. It's advisable always also to use a data cable type, which is with twisted pair and internal shielding option. And good luck. That's all, and thanks very much.